All right. Thanks everybody for coming. Very happy to be here again, second time for me at MRMCD. And I would like to talk today about data visualization and how it may help us to see patterns in chaotic and complex data sets. So first, the obligatory who am I? So I actually started out in academia. I studied biology for bachelor's and master's, and then when I did my PhD, I really fell down the whole math and theory rabbit hole and never really managed to escape that. So I did research on cancer, in fact, so optimizing treatment regimes and finding doses and things like that. And the key point here is that I mostly did stuff with like pencil and paper or on a blackboard, so proving things theoretically, but also did analysis of some larger data sets. And afterwards, I went into industry, where I'm de facto basically doing data science for a living, and that obviously also comes a lot with dealing with larger data sets and trying to figure out something based on them. And of course also, if you find out something, communicating it at least as effectively as possible to colleagues and also to non-technical folks. So because of that, I spent quite some time over the years thinking about and learning about how to communicate, or how to find insights in data sets and then how to communicate them to other people. And something I'd specifically like to talk about today is visual communication for a number of reasons, which I will go into in a few seconds, and how visual communication or visualization of data can actually help us get new insights and validate them based on data sets. And to motivate that, I always like to start with some examples. And the first one is one taken from history, the history of medicine actually. From the mid of the 19th century, there was a by now very well-known cholera outbreak in a part of London called Soho. And over the course of that, more than 600 people died. But back then, people did not really have that much of a good understanding about infectious diseases and transmission of diseases and things like that. So it wasn't really quite clear what exactly was happening and who or what was to blame. I found this historical picture here to kind of make the point that back then, this was actually pretty much a terrible disease to have. Today, if you have cholera, it's actually quite easy thing to cure. You need to make sure you drink enough because you will lose lots of water. Except for that, you actually have quite good chances. Back then, because medicine wasn't as advanced as it is today, it was pretty terrible to get cholera, and subsequently many people actually died from that. And the example I would like to talk about now is based around this fella here, who has the very cool name of John Snow. He was a medical doctor, and he studied what happened there. He wanted to figure out what exactly was to blame. And of course, every day, authorities would collect all the cases that they heard of and collated them into large lists. I found a modern version of such a list here that lists the cases and the number of deaths and at the longitude and latitude, so the coordinate of the different places in the city. And of course, if you just look at this list, it's very long, over 600 entries, of course. That doesn't really tell you anything at all. So you see, of course, obviously, they're all in the area of London, Soho, but based on that, you could stare on this very long list, and I think it would be quite hard to figure out if there's any pattern or meaning in these data. And what John Snow then did was, well, in hindsight, a kind of trivial thing, but back then it was pretty revolutionary. He got these lists, looked up all the addresses from those lists, and he drew a map that looked like that. Of course, back then, 1800 something, we didn't really have 4-color offset prints, so it was more like a black and white kind of thing. Kind of not really that nice on the eyes, but if you look at the map a bit closely, then you see what he did is that at every house, when there was a case, he added a little black dash. And you can see, just by squinting at the map, you see, well, lots of things seem to be happening here. This house here really seems to be affected a lot. And the more you move away from that, the less cases you observe. Okay, so that's quite interesting. And what makes this a little bit more obvious is this modern redrawing of the map that was done by a cartography firm, also from the UK, Merit Cartography. Apparently there's actually companies that draw maps for you, and they did this like just to show off their skills. And they use the color coding that's a little bit nicer on the eyes, because they used red to mark the cases and the green background. And I think, or I would say it's pretty obvious that in this visualization the cases pop quite a little more, and you instantly see, well, here seems to be happening a lot. The most is happening here. There is a suspicious dot. We will talk about that dot in a few seconds. But you can see there's like a kind of center of gravity where most of the action seems to be happening. So it might make sense to go there and check out what exactly is happening. And if you really want to drive this point home, that exactly there is something happening, we can even use a much more mathematically involved visualization. This one is called a kernel density estimate. Doesn't really matter what exactly it means. What it does is it colors every pixel on the map based on the number of cases in a small vicinity around that pixel. And what you can see there in the middle, this lovely red-yellow thing blooming up, I would argue it's pretty clear that this is really seems to be the point where it's happening a lot. And what you see right next to that is this white P on a blue background. Keep in mind, we're in the 9th century, so parking lots were not a thing. So this P does not refer to a parking lot. Instead, what it refers to is a pump, a water pump. Back then, people would actually get their water from such public pumps. And what's quite interesting is that many of these cholera cases are very, very close to this one specific pump that's still there today. It's actually a replica. It's not the original one, but it looks exactly like the original one. You can go there and take a look at it. And what's also very interesting to see is that this handlebar here that should be here is missing. That has a specific reason in history, because when Jon Snow saw, well, not this map, but the black and white one he realized, well, there's this pump, something is happening around that. And then he actually talked to all the people that had cholera and were still alive. And as it turns out, every single one of these cases reported that they got water from this very pump in the middle. So that was kind of smoking gun evidence, but one thing wasn't still clear, because in some cases, there were cases where another pump was closer. So here are some cases, and they're much closer to this pump than to that. And he talked to all the people who were closer to another pump, and they all said things like, well, yeah, we have our own pump here, but the water isn't really nice. But you know, the pump in Broad Street, that has really good water, so we always let our children fetch our water from the Broad Street pump. And it may very well be that the Broad Street pump had quite delicious water, but it also had quite, well, not so nice water on your health, because as it turns out, the cholera outbreak did indeed originate from this pump. A few months later, they dug up the earth around it, and what they found is there was like actually a hole that people used to do that back then, a hole where they dumped all their trash in it, and once the hole was full, they would just dump some earth over it. And as it turns out, what they found in there were used diapers from a little child that died a few months before, and the little girl died of cholera actually. And now we know, well, the water apparently got into that hole and washed out cholera, and then put it into the water canals or water pipes in the surrounding, and that's how exactly it was transmitted. And the popular version of the story goes that he took his map to the mayor, and the mayor was like, yeah, no, I don't care. We need to keep the pump running. But I looked it up, and the truth is actually the mayor had understood it, and he was like, okay, yeah, that makes sense. We should disable that. So he did not, as some stories go, had to travel there secretly at night and steal the handlebar, but it was officially moved. And at that point, no new cases were noted. So apparently, yeah, that was pretty much what solved the problem. So this is one of those cases, I would argue, where, well, based on perspective from back then, a very clever visualization, based on today's perspective, a pretty straightforward visualization, really helped us, or helped those people, to gain a very crucial insight with direct consequences for many people. A second example I would also like to show is a made-up one. It's from a statistician called Anscombe, rather modern fellow. He did this in the 70s. He was a classically trained statistician, so he learned how to do stuff with pencil and paper. And back when those modern computing machines became a thing, he was one of the few people who thought, hey, that's a cool thing. We maybe should learn how to use that for our business. And he constructed an example data set because he wanted to prove a point. What he noticed is that many of his colleagues would get a data set and they would instantly start doing some kind of calculations with their computers. So they would compute stuff, but they wouldn't really interact with the data. They wouldn't really look at the data or make plots. And he wanted to prove to his colleagues that, hey, maybe it might make sense to first, if you get data, step back, look at the data, and before you turn to your computing machines, maybe draw some plots. This data set that he made actually consists of 4 different ones. Data set 1, 2, 3, 4. And it contains pairs of numbers x and y. Those are completely made up. There is not any single deeper physical or biological meaning behind them. He made them up sitting at his desk. And if you just look at these data, if you were given them based on full transparency, you can say, well, you can see all the data, but it doesn't really teach you much. Interestingly, as a kind of little Easter egg, what Anscombe did, he constructed those data sets in a way that nearly all of their statistical properties, those things that his colleagues would focus on a lot, are completely identical for all 4 data sets. So you can calculate means and variance, correlation coefficients, you can fit like a linear regression line. It's all the same, either exactly or based on multiple decimal places. So he actually made this like a little bit to trick his colleagues to say, well, imagine you have a data set that has these properties, what can you say about this? And when his colleagues took guesses, he was like, actually it's 4 different data sets, and they're vastly different, because if you plot them, that was his point, you see instantly that those 4 different data sets have fundamentally different qualities. So let's maybe look at the first one. This is a very classical example of a data set that you can very often see in science. You have these 2 things. They're somewhat linear related. Of course, there's like a little bit of noise around that, but that's just because nature has noise. That's fine. So in that case, this linear model is a perfectly valid thing to do. If you plot the second data set, you see something completely different. And of course, you can again construct this linear model, this blue line, but the moment you see the data points, you instantly understand it would be completely nonsense to fit this model, because those points are not in any meaningful linear relationship. It seems to be more like a quadratic thing. The third one is also quite interesting, because the third data set has a very, very nice, extremely clear linear relationship, but there is this one single data point that is an outlier. And I'm pretty sure if you were just to look at these raw numbers without the plot, you would have a pretty hard time instantly identifying this point as something you may want to look again into. So maybe there was a data entry error or something, or you messed up in your notebook or whatever. And the fourth one is also a funny one, because what you can see here is, again, you can very much compute such a linear model with your statistical software of choice. But what you see is, except for this one very, very weird outlier that may very well be a mistake, there isn't any relationship between these 2 variables, because for very similar numbers of x, y varies quite a lot. So this was Anscombe's point, like, look at your data, make clever or make at least any visualization and think about that, because your brain is much more powerful than these modern newfangled computing machines you can use. And only if you have made a visual understanding and know what's happening, then you can turn to your computer and say, well, for the first one, please make a linear model for me, because that seems to describe what we're seeing. For the other guys, you definitely want to first interact with your data a little bit more and think about what is happening. Okay, so in the course of these 2 examples, what did we just observe? Well, I like to quote this very famous sentence, der Mensch ist ein Augentier. It is often attributed to Goethe, the famous German poet. I think it is not proven that he ever said this, though, but I will say it anyway, because I think it's nice. Like, this is something that people have been knowing for centuries. This is like kind of like a sentence people keep saying. And what they mean is something that modern neuroscience and psychological research very much has proven by now. For instance, there's this one paper that has shown that approximately 90% of all the information that enters your brain at any single second is somehow related to visual things, so to your eyes. All other senses combined, hearing, smell, taste, proprioception, touch, everything else is approximately only 10% in sum. And in fact, 50% of the entire brain surface area is somehow directly or indirectly related to your sense of vision. And 66% of everything that your brain is doing, like 67% of your clock cycles, so to say, are spent on looking at visual cues and making sense of visual cues, as long as your eyes are open. Of course, if you close your eyes, this number will drop. But in a normal wakeful state with open eyes, your brain is very much preoccupied with making sense of what you see, and not so much at all with everything else, like what you hear or what you smell or whatever. And this leads to this very, very cool finding that the human brain is able to process images by multiple orders of magnitude. People say like 60,000 times faster than text. And I think we have seen this when we saw the table earlier, and then afterwards we saw the plots. I would say we instantly reached an understanding when we saw the plots. But if we were to only look at the table, we would have need to spend way more effort thinking about this table and trying to understand what this is that we're actually seeing. Okay, but some forms of visualization, as we have seen with the Jon Snow maps, seem to be more effective than others. So if you remember when we saw the map from that cartography company that added color, I would say the cases popped much more into our eyes. So it was certainly easier on the eyes than looking at the original Jon Snow map that was drawn all black and white. And the third version that we saw with this kernel density thingy that really identified a very, very small yellow reddish blob where most of the action was happening. So different forms of visualization seem to be more effective for certain kinds of messages than other ones. And the cool thing is, and this is the main part of the talk, there are actually studies, there's proper research on it, which forms are good for which use cases. So we can actually learn how we can make a good job at this task of visualization of data and trying to glean insights from looking at data visualizations. And what I'd like to start with are two very simple rules of thumb. They're basically only my personal opinion, so I do not claim that those are in any way optimal in any sense of the word. They're more like received knowledge of doing data stuff over the years. But I think these two very non-technical, very simple rules already go a very long way. And if you're aware of them while you're doing data visualization, then you already move a long way to your goal. So the first one I'd like to always call, with a nice keyword, simplicity. What do I mean with simplicity? Well, I would always recommend to start with the simplest analysis possible. So if you have a huge table with many, many columns, it very much makes sense to start small. Look at maybe only one of the single columns or subsets of your data set if you have millions and millions of entries and cannot look at all of them at the same point of time. So by starting with very simple analysis and then gradually building up our visualizations, we also gradually build up our understanding, our mental model that we have of the thing we are looking at. If we start with the most complicated possible diagram, plotting everything against everything, we tend to be overwhelmed. So we will start simple and gradually build up complexity. And when we're doing plots, we should start with the simple ones first. Ideally, we should always do what we just saw earlier, plot the data directly, every data point as a point. Because if we see the data points in their raw form, we see the most information. We can, of course, plot like a linear fit to it, or we can plot averages or whatever. That's all fine. But those are always mathematical abstractions, and they always lose a bit of information. So whenever possible, really go to the raw data and look at the raw data before you do anything more mathematically involved. And the second rule of thumb, I was also able to find a very nice buzzword for it. I have to apologize in advance, it's mindfulness. It was the least bad word I was able to find. What I mean with mindfulness just means whenever you do a plot, be mindful, be aware of the fact that this plot is able to tell you one thing or a set of things. And you should always be aware of what this specific plot that you're doing right now, what it is supposed and able to tell you. And of course, also the converse, what it is not able to tell you. And if you know that you're making a certain plot that is supposed to tell you something, then you know you can remove everything else from that plot that is not directly relevant. And this makes it much more easier on our eyes and much more easier to process. And like I said, the converse is also true. You should also be able to always understand what a specific kind of plot is not able to tell you. And this always gives what I like to call rise to natural follow-up questions. So if you made a plot and you say, well, this plot is able to tell me so and so, then it makes sense to think about, okay, but what am I missing with that plot? What would be interesting follow-up questions? And in this way, you're kind of entering a kind of dialogue with your data set. So you start by asking simple questions, you get an answer. You think about that. It's like pretty much like getting to know a person. And by learning a little bit, you have, well, your brain will often say, well, but would be nice, interesting follow-up questions to also know what this and that means. And then you automatically know what interesting next questions or next plots might be to do. Okay, so to get a better understanding of what exactly this means and how we actually do it in practice, I would like to start with an example data set. And this is a very, very, very famous one. And this is one of those like big 5 data sets that you will always see sooner or later whenever you are learning about data visualization or machine learning. It's the famous IRIS data set by a famous guy, Ronald Fisher, in the 30s. He was a statistician. He did lots of very cool things in statistics. He also had some not so cool political views, but shouldn't go into detail there. But this data set is very interesting and very, very easy to understand, I would ask. What he did is, or what he actually told his research assistant to do is, he said, look, there's this patch of land, 3 different iris species, different species of plants from the same genus are growing here. From every plant, please harvest a bunch of leaves and measure them. In particular, what he said is what we would like to do is we take from every plant a petal, those are those huge leaves on top, and also a sepal, those are these plants, those leaves lower. And for each of those, we measure both the length and the width. And for every of these 3 species, please harvest 50 different plants. So this means we have a data set with 150 rows, 3 times 50. And for every of these rows, we have 4 numbers. So from the sepal, the length and the width, and from a petal, the length and the width. And of course, they also wrote down, obviously, which kind of species that was. And if you think about a little bit about this data set and try to freely associate, I would say you can come up with many, many different interesting questions you could try to ask this data set. The one single question everybody always does, and we will also do this one, is based on those measurements. So if I were to measure a new plant and give you those 4 numbers, can we reliably identify or infer from which of these 3 different plant species these leaves might have come? This is like the typical one that always this is the typical thing that is always taught in like machine learning 101 courses. Of course, like I said, there's many, many other different things you can do with that, but let's focus on the canonical example. So, like I said, we would always like to start simple, and we begin by only looking at one variable at a time. And like I said, by directly showing the raw data. We have 3 times 50 data points, that's not really much. We can easily plot all the data points as individual points here without running into issues of overplotting. If it was like 50 million points, then you wouldn't see anything because it would like just be a huge blob. So we plot those 4 variables, the 4 columns, one at a time, 4 different plots. And we already see something quite interesting. Because if our goal is to, based on the numbers, infer the species of a new plant we haven't seen before, then we see some of these variables, some of these columns seems to be significantly more useful than other ones. In particular, those 2 things, petal length and petal width, they seem to carry much more information because the 3 different species have much larger differences between them. The sepal ones, however, well, you see there's certainly some signal hidden in there. You see the groups are a bit shifted against each other, but for instance, if I would say, well, I have a sepal that is 3 centimeters wide, we could only guess, well, it probably might be a versicolor, but it might just be everything else too. But if I would say, well, we have a petal of length 2 centimeters, we could be very, very sure this is most likely taken from a setosa species. Okay, so we already see by just looking at one variable at a time that some of these variables seem to carry much higher amount of information, but nonetheless, by just looking at a single variable at a time, there's not really a reliable way to always tell 3 species apart. So of course you can say the setosa one is always doing its own thing. If we have tiny petals, we can be pretty sure it's a setosa, but there's in the middle kind of zone of overlap where it's not quite clear. If I would say, well, we have a petal of width 1.5, it could be either of those. So there's still a little bit of uncertainty zone in the middle, but except for that, we're already doing a pretty good job just by looking at one variable at a time. Now, the natural follow-up question I've posed earlier is always, what can these plots not tell us? And I guess it's pretty obvious if we say we only look at one variable at a time. This cannot teach us anything about whether those 4 variables, those 4 columns, are in any relationship with one another. Or put differently, if we were to consider multiple of those dimensions at the same time, would we maybe be able to see even stronger differences? Would there be additive information that would make it easier for us to tell those plant species apart? So, and if we do so by moving to a 2-dimensional space now, we indeed see some more patterns emerging. So let's start with the 2 sepal columns first and plot them in 2-dimensional space. So now we see the sepal length is on the x-axis, the sepal width is on the y-axis, and those 2 guys are now occupying my 2 dimensions I have on a piece of paper. So to encode the species, I have to use a different kind of encoding. And in this case, I used color because I personally felt this Python matplotlib standard color cycle does a decent job, blue, orange, green. But the last time I gave this talk, one person with one kind of color vision deficiency told me for him, the green and the orange one actually, they aren't really distinguishable. So that was also a learning from me. So maybe don't do the standard color cycle, but there's by now color cycles that are optimized for people with vision problems. either way, I hope we can all see this. For those that maybe cannot, I can say the blue one here is clearly separated, and the green and the orange one are not separated at all. They're very nicely intermingled, or very badly, depending on your perspective. Okay, and what we could also do to encode this variable of species, we could, for instance, also use, instead of colors, different symbols. So for instance, here for Setosa, I've picked a rather large dot, for versicolor, the little cross, and for Virginica, the little square. And something I notice here is that I always feel my attention being drawn to the Setosa one, to the ones on top here, because those symbols are they have the same dimensions, they're the same size, but because it's such a large blob, it kind of dominates the picture for me. A similar or even worse problem occurs if instead we plot them all as dots, but we use different sizes of the dots. Then my eyes at least are always very strongly drawn to this blob here, although that's not at all the purpose of the plot. And even worse, if I see this plot without really thinking about it, I would say the point size encodes some continuous trait, some number. And whatever that trait may be, the Setosa one have clearly more of that because there's larger. This is my naive interpretation. I would argue it sounds a bit naive if I say it like this, but I would say many people would agree for me. If they don't know this, they would say, well, yeah, there's some 2D space. Oh, I cannot cover that. I'm an idiot. I would say it's ignore that. Now it's covered. Perfect. No, but like I would say it's a very natural interpretation to say, well, size, continuous variable size, it's a number. It must be related to some continuous trait. Like, I don't know what continuous traits of a plant you could have. Like, I don't know, maybe the root length or whatever. So to encode this, what's called a categorical variable, where you have like 3 different things, Setosa, versicolor, virginica, I would argue color is, in this case, the best thing to do. This one here kind of gets iffy already, and this one does not at all suggest a categorical variable, but it does instead suggest to me very strongly a continuous variable, a number, 3 versus 3.5 or whatever. So depending on the kind of variable you want to encode, different ways of visually encoding seem to be more versus less appropriate. And of course, based on our analysis objective, what we see, the sepals aren't really doing a great job. Of course, Setosa is nicely separated. You could draw a very nice line here and say, well, if you're in this space, it's likely Setosa. But those guys here, they're intermingled. So if you're in this space, well, who knows? Could be anything. And yeah, like I said, some ways of encoding categorical data are much easier to grasp visually, and some of them bias attention towards certain things, and some of them, in my opinion, are outright misleading. Okay. What is remaining to do? Well, we have just looked at the sepals, so maybe let's examine next the petals and hope we may be able to learn some more. And lo and behold, we actually can. Because if we plot the sepal length and the sepal width on the 2 axes, we again encode using the color, the species, then what we can see is we see a very, very nice and nearly perfect separation. We see again, Setosa seems to be doing its own thing, and the other 2 guys, admittedly, there's a little bit of overlap here where we can't really be sure, but if we're in this blob here, we can be, I would say, very, very sure it's a versicolor species. And if we're in this blob here, we can be reasonably sure, well, that plant you have given to me with those numbers seems to be very likely coming from a Virginica plant species. So the petals make all the 3 species nearly perfectly distinguishable, which is nice. And based on our initial analysis objective that we had, we could say here, okay, we can call it a day, we're done. But maybe still, let's continue thinking about this a little bit. We can see a lot of other different things. For instance, there's a very clear correlation between these 2 things, consistent across species. I don't know why. Despite being a biologist, I had never really enjoyed plants, and I was quite happy when I was able to drop plants from my curriculum for good. A plant biologist might know, but that's an interesting question that just emerges because we looked at the data. That's interesting. Maybe something to look into. And what's left to do? Well, we have looked at the sepals and the petals individually, 2 against, one variable against the other one, and another one against another one, but the cross combination of them is missing. So what we now also could do, if we were so inclined, we could do the 4 remaining plots where we plot 1 sepal trait against 1 petal trait. And then this comes out. It's also interesting to look at, I guess. We see petal and sepal traits seem to be not really strongly correlated. Another question I cannot really answer why. Maybe a plant biologist could, but maybe again, avenue for further research. Who knows? But I would like to stress a kind of meta observation here, which is that we only had 4 variables in our plot, in our table, but we already had to look, bless you, had to look at 6 different plots already to plot all of them, and that was only in 2D space. We could also go for like 3-dimensional plots and maybe think about clever ways to plot even all 4 at the same time. Not quite sure how we would do that, but the number of plots we can do increases actually at a factorial law, so very, very fast, in the number of variables we have. And this is a little bit of a problem if we have larger data sets. So looking back first, we have distinguished categorical versus continuous variables, and we have learned that different kinds of visual cues seem to be more appropriate for either of these. And actually there's psychological research on that, and we will look at that in the next section, because people have actually painstakingly measured people's responses to what works best versus what does not really work best at conveying messages. And like I said, more variables means we have more plots to inspect. That's a little bit annoying. There are ways around that, and how exactly we will see in the section after the next one. So let's talk about those results from psychology. And there is this very, very famous paper by now. It's a classic by 2 psychologists, Cleveland and McGill, from the 80s. And they had this idea, if we want to visualize continuous data, so numbers, not categories like plant species, but if we just want to visualize numbers, we can think of many, many, many different ways to do that, but are some of those intrinsically better defined as being able to tell or convey these informations more accurately? And being psychology guys, they just, well, they voluntold a bunch of undergraduate people and said, well, you'll get some course credit, but you need to participate in our very important research. That's actually a classical thing to do if you study psychology. And after doing that with many, many people, this by now very famous diagram came out of it. This is really classic in data visualization circles. And this is what they call the perceptual ranking of visual differences. Or to put it in less fancy words, it means what works good versus what doesn't work well. And what works good or what works well is on the top. So what they found out is that, for instance, to convey numbers or to be able to compare numbers against each other, it makes very much sense to place them along a common scale. So is there actually some, no, there is no, I'm very much a fetishist for blackboard drawing, but there's no chalk. So I'll just, we have to, right where? Oh, lovely, yes. I love blackboard drawings. This is really my thing. So to illustrate this briefly, if I just have like a 1-dimensional axis and I have 2 points, I would say it's trivially easy to see which of those guys is larger. If we know the orientation goes like this, right? So this is larger, this is smaller, then I guess nobody would disagree that obviously A is smaller than B. So this works really, really nice. You take one look, you instantly know, okay, A is less than B. Length is also nice. So if you have like a bar chart and you align all of them at a common 0, that's the important point, then it's trivially easy to see, well, this guy is most definitely larger than that guy. Okay, but the moment you get rid of this common alignment and you're at the second thing in the visual hierarchy, where they're all over the place, it becomes a bit harder. So you can still see, well, this guy probably seems to be the largest, then maybe this one, then probably that, and then I would argue that one, and then this. But I have to think about it a few seconds and have to like kind of try to mentally align them. So if we get rid of that, it becomes already a bit harder to convey accurately which of those guys is the largest one or which comes first. What's even worse is angle, number 3. There's also actually an evolutionary explanation for that, because if you think back when we were like hunter-gatherers and such, it was quite useful to be able to tell apart different lengths of things. So if they're like a very long snake, you may want to run off. If there's a short snake, I don't know, might be not so terrible, except if it has, I don't know, a certain color. We will talk about color in a second. So it was quite useful. Or if you say, well, this fruit is much larger than another fruit, so it might make sense to eat the first one. So we are kind of hardwired to be able to tell those guys apart, but I cannot really find any example why it would have mattered in our evolutionary history to be able to tell apart angles. And in fact, we can do it if it's like so. It's quite obviously this is the most narrowest one, then this one. But if you see these kind of pie charts that like manager and suit and tie people love, and then you have like things like that, it looks like so, and it's quite hard to really say which of those are the smallest and like what's the order in there, because it's not anything we are in any way hardwired or optimized to do so. yet even worse is area, and the most terrible one is volume. That's because the area scales in the second, what's the English word? Power, thank you, yeah. The second power, and volume scales in the third power of the length x. So if you say, well, we compare this guy against that guy, okay, you can say, well, that one is obviously larger than that, but it doesn't really seem that much larger compared to that, but in fact is, because this scales at x squared. So this x may be a little bit larger than that, but this x squared is already significantly larger than this guy here. And if you have a cube, it becomes even worse. And I noticed that again, suit and tie people, they have to take the piss here, I'm sorry, they love these volume things. I don't know why, but like I guess it's because like in PowerPoint there's like the standard graph selection thingy, and they say, oh yeah, when I have like these huge cubes, they're awesome, and we have like here our raw earnings, and then like my department which has the largest earnings or whatever, and they use these volumes and cubes, and yes, it may look nice because you're plotting lots of ink on the paper, and that makes a lot of impact, I guess. But from a scientific and data communication perspective, please don't do that. Stay to the boring things, because in this way you can actually convey information in an accurate way. I already mentioned we're talking about color at the end of this chart. First, let's talk about the saturation. In this case, well, it's a very nice example. We can still say, well, that black here is the darkest, then probably that guy, and finally this. But if you have numbers that are not that far apart, looking at the saturation of colors, it becomes harder to really say which comes first. And the color hue, again, for continuous variables, for numbers, it doesn't really work at all. So here again, this is a nice example where you can still say, well, this is a cyan, then maybe this bluish thing comes, then the slightly darker blue, and this green is doing its own thing. But imagine you are like visualizing 9 different numbers that are all quite close to each other, and you use slightly different changes of blue. It is really a pain in the ass to really say this one comes first, then that one, then that one. So colors are not at all useful for conveying continuous variables. However, we have seen earlier, colors can really shine, namely when it comes to categories, so categorical data, different species of plants, for instance. And color, in fact, is immensely powerful. Our brain is really hardwired to understand color, especially stark color differences. Again, maybe we can spin up some story from our evolutionary history, maybe thinking about recognizing a ripe fruit. If it's nicely red, it probably is juicy and delicious to eat. If it's green, we may still want to like wait a bit. Or if there's like some lizard which has like a yellow and black pattern, I don't know, maybe experience has taught us to kind of stay away from that guy. So color in itself is nothing to be hated, quite the opposite. Color is lovely, but it is very powerful, and that way, that's why we should use it sparingly, again, in an also mindful way, and primarily for categorical data. So here's some do's and don'ts, some patterns and anti-patterns for the use of color. One thing I see people often do, especially when they just discovered that Excel has the opportunity to generate plots automatically, they color every bar in a different color. And in and of themselves, that's needless, to say it in a very polite way, unless you are actually conveying information. If those colors are linked to something in some other plots that use it the same color, that's lovely, then the color actually has information. But if you just use colors because you like them and you like a wonderful, colorful chart, please don't. It's ugly. I mean, first, it's very ugly because these colors clash with each other, in my opinion. It's not nice to look at. And secondly, it is just unnecessary mental overhead, because people will see this and they wonder, yeah, okay, but like, does the green mean anything? Does the red mean anything? Is red in any way like more than green or anything? It's needless. It doesn't make any sense. And if you don't need it, get rid of it. If, like I said earlier, if we can use an easier way to convey numerical differences, like a bar chart with an aligned 0, then use that. This is a very nice example of what does not really work, because you can say this one seems to be the smallest, and then it's kind of unclear. I think that one comes first, then that. But those numbers are so close to each other, you really need to focus and stare intently to see which comes first. This one is much easier. Like I said earlier, if you use color, please be consistent. So here we compare something related to penguins and dolphins. Here we have marked the penguins in blue, the dolphins in gray. And in the lower panel of the figure, penguins are gray and dolphins are yellow. This doesn't make any sense. In fact, it confuses me, and I will see this and I wonder what was the person thinking. And of course, I will try to take the person seriously and think, okay, he probably had a very good reason to pick these colors, and I will try to figure it out. But at some point, I realize it's nonsense. Much more easier to read. We use a consistent encoding. We use blue for penguins, gray for dolphins in all of the figures panels. And also interesting to observe, we are drawn to colors as opposed to grayscales. So in this panel, we instantly give more attention to the penguins. And if that's the point, if we have an article about penguins where that's the focus of our interest, then this is a lovely thing to do, because we are instantly drawn to the penguins and see, okay, the line here, the bar there, they correspond to each other. Everything is lovely. And the last thing, this is also related to what I've said earlier here. If we have some kind of categorical color palette, we need to make sure that people understand if there's some ordering or not. So if we talk about different plant species, like 3 different species of iris, there's no obvious order. Like Iris setosa is not in any way larger or comes first compared to Iris virginica. So in that case, we would use a color palette that makes this clear, because it is obvious that there's no relationship. We cannot meaningfully say blue comes first, then yellow, and then green last. So this color palette makes that clear. However, if we use one that has different hues, then people will instantly see or think, well, the light one probably comes first, then the medium one, then the dark one. So this always implies some kind of ordering. If there is an ordering, if, for instance, you compare, I don't know, the personality traits of maybe children versus teenager versus adults versus very old people, it may actually very much make sense to use some kind of hue color scale thingy to make that point, because there's a logical natural order. But if there's no order, like in our plant species, well, then don't do that. Okay, the second thing we have observed earlier, that's the section after the section, is what's usually called the curse of dimensionality. What I've said, if we have many columns, it becomes much harder to really look at all of them. So some first ideas what we could do about that, well, we could pre-select those volumes or those columns that look meaningful to us. So we saw earlier, well, the petals seem to carry information, the sepals not, so maybe just discard the latter one. You can do that, but you always implicitly hope for the best here, because if we just look at all the dimensions individually and say those guys don't seem to carry much information, we discard them. We never verified, maybe they also carry information in a higher dimension. Like we've seen in 2D space, more patterns can become obvious. What we can also do, if we see some variables are very, very strongly related with each other, then we can say, well, if these two columns always pretty much say the same, we can lose one of the two, because apparently it doesn't really carry much more information. We'll see an example of this in a few seconds. Of course, we can always say we can use some fancy machine learning model, algorithm, whatever, to try to figure out which of the 30,000 different columns carries information. I don't want to hate on that. I do some machine learning research myself, and I think it's a good thing. But my point is, some clever ways of visualization can also work as well. Sorry? I know. I'm very well aware, yes. You can, but I will not always hate on it, because in some cases, if you know what you're doing, it's also quite useful. But be mindful. Oh yes, I mean, we'll talk about that, about correlations. It comes in a second, like I said. Okay, to come directly to that point of variables being correlated, being spuriously correlated, or correlations being, or things actually being hidden by correlation, we have another classic data set, that's the diamonds data set. And this is a bit funny, because I did a lot of research, but I was not able to figure out who the guy was who actually assembled that in the first place. What I only was able to find is it was originally sourced from the Lose Diamond search engine. Apparently there's like some kind of Google but for diamonds. And some person apparently had lots of time and sat down and Googled the shit out of different diamonds and wrote them all in a table. In fact, that person was very motivated and queried over 50,000 different diamonds. And for every diamond, they wrote down a bunch of things like karat, that's the weight. The cut, there's different ways of cutting a diamond. Some of them are like more beautiful, I guess. The color, there's better colors and worse. I guess that makes sense if you have like a really, really nicely non-colored transparent one. I guess that's in some way more beautiful than like some kind of muddy grayish one. The clarity, like how much gunk is there in it, like sand or minerals or whatever. And some other numerical variables that seem to be only understandable with diamond business domain knowledge. Apparently, like if you take the total depth percentage by dividing Z over the mean of X and Y, apparently that's a number jewelers care about. I don't know why. It's a thing apparently. The price, that's what we care about in our example, and the measurements in 3 dimensions. So this is our table. Looks somewhat like that. Again, this is one of those huge tables where you can scroll through and try to figure out something, but it's not really quite obvious what is happening here, especially if you have 53,902 rows. And one thing that I have learned in my PhD days, actually, when I also dealt with large tables, I was looking at data sets that describe the gene activity in many different cells from a human sample. And the human body has 30,000-ish genes. So I had like tables with 30,000 columns and a few thousand rows maybe. One thing when I was overwhelmed, my professor would always say, have you considered making a heat map? He always said that. And it was actually the right thing to do, because a heat map is indeed a very nice map of the data set. So what we do here is we put every entry of the table in one thin line here. And what I've also done is I put them all on the scale from 0 to 1, so we can use a like unified color map for all of those columns. And because let's say we care about the price, because let's imagine we are like in the diamond trade business and we care about the diamond price and we want to like predict a price of a diamond, I have sorted this table also to make the most expensive diamonds appear on top. And now we can just look at this nice map of our data set and we see already some interesting things. So for instance, what we see is the carat, the weight, seems to correlate with the price column, because the more to the top we go, the more the carat seems to increase. It's not a perfect trend, certainly. There are some bands in between, but there seems to be something happening. Also interestingly, X, Y, and Z, the 3 measurements, they also seem to be correlated because they all grow the further to the top we go. Interestingly, they're all very, very strongly correlated with one another, which again makes sense, I guess, because I think it's quite unrealistic to have a diamond that's like, I don't know, 20 centimeter long, but only a few millimeters wide. That doesn't make sense. So it kind of makes sense, yeah?
How do X, Y, Z correlate to the third group of characters?
That's a good question. We can calculate that later. Probably they will correlate in some way, yes, because of course the volume via constant density will lead to the weight in carat. So the point here, however, is, and I found this quite interesting, that other things like the cut, the color, the clarity, apparently they aren't really correlated with the carat, which I found with the price. Sorry, which I found a bit confusing, because my layman's understanding of the diamond business was that if you have a diamond that has a very, very beautiful color, that's very, very clear, really transparent, then it should be much more expensive than one that has like lots of gunk and dirt in it. So we do know this, I would argue, like at least on an intuitive basis, but right now we don't see it. In a few seconds we will see it though. And like I said, assessing those correlation patterns, well, if you have 30,000 human genes, it becomes a bit more tedious, but it's still better than looking at a raw table. And in this way, a heat map is always a good first starting point. But like, if you want to look at the entire data set, you run into some scaling issues. So some other things may be worthwhile doing. So what helps, for instance, is not looking at the raw data, but computing correlation coefficients between these different columns. And if you can do that, you see something that we have also by inspection just seen now. We see X, Y, Z, and price. They're all very, very tightly correlated with one each other. And those 4 guys are also all tightly correlated with the weight in carat. The other stuff we again see, there isn't really much of a correlation happening. In fact, sometimes there seems to be some kind of anti-correlation, weirdly enough. So diamonds that have a larger clarity seem to be smaller. We'll also see why in a few seconds. We use, as you can see, a different color map here. We don't use a continuous one like before, but now we go from red to white to blue. Does any of you have any idea? I guess it's pretty obvious, but why would we do that? We are dealing with correlation coefficients here. So that means that if we have two variables, they can be positively or negative. Yeah, any idea? Yes. Exactly, it's an anti-correlation. So the 0, 1 is like a natural midpoint, because if you're close to 0, those 2 guys don't do anything with each other. But if you're really close to -1, they're perfectly anti-correlated. So one goes down, the other one goes up. So it makes sense to have a color scale that is much more intense towards the edges here. Okay, so something you can also do is if you see this table, you can also say, well, dear computer, can you group to me everything that is somehow correlated with each other into clusters? That's there's some mathematical machinery behind that, so if you want to do that, please read into this and be aware of what you're doing, because there's ways to fuck this up. But if you do it the right way, then the computer will happily say, yeah, sure, there's this cluster of price, X, Y, Z, and carat, and this cluster is very, very tightly correlated within, and everything else, kind of doing its own thing. So cluster map is something to keep in mind, maybe, but like I said, read the docs for that, because the stuff can happen. And to cut a very, very long story short about the cut and the color and the clarity, which we have seen before, were apparently not correlated with the price. They actually are, but it is hidden by the stronger correlations we have seen before. They're, I guess you could call it like a kind of secondary or modifying factor. And if you again do a very, very simple visualization by looking at the price as a function of the weight, and then you color code those other guys, cut or color or clarity, especially for clarity, you see very nicely, well, the larger or the more heavier the diamond is, the more or the larger the price will be, but the clarity influences that. And the very high clarity will always shift the price somewhat upwards. So there is in fact very much a correlation between price and clarity, but it was just overshadowed by this much stronger correlation between price and weight. But if we use this kind of more involved visualization, then we do see, okay, this is like just a secondary factor acting on top of that. Also, another thing I found quite fun, actually, if you look here, you see exactly at 1 carat a very, very sharp increase in price. I wasn't aware that's a thing, but apparently we see it quite clearly now. And I guess that's due to marketing psychology of jewelers, because there's always like this, well, if you want to propose to your sweetheart and give her a beautiful ring, well, better should be 1 carat. You don't want to be a cheapskate, right? And in fact, many people say, well, darling, it really needs to be 1 carat. Well, like, you don't want to be cheap on me, right? So the market for 1 carat and above diamonds is much more expensive than the other one. I think we're coming to a close already, so I should speed up a bit. The last thing I briefly want to show is heat maps are also nice for time series data. There's this very, very famous airline passenger data set. It's a bit older now, but it plots over the years the number of passengers starting from the USA or traveling to the USA, and we see it goes up overall, but there's like some oscillations. And I found this heat map here online that plots the time not on one axis, but in 2D space. We have the year on the y-axis and the month on the x-axis. And then you see a beautiful pattern emerging, namely that in the summer month and also a little bit in December, the number of airline passengers strongly increases. And that, of course, makes sense. People want to do their summer vacation, and maybe when it's Christmas time, they want to return to their families. One thing I'd briefly point out here is I stole this plot, and I have one critique to make for this specific plot, and maybe you're able to spot what exactly I take offense here with. Is it showing offense or? Oh, yes. Yeah. Yeah. It's completely, exactly. It's completely nonsense, because it implies there would be some kind of natural midpoint at like 320. We'll be done in a second. I'm incredibly sorry. Which is obviously nonsense. Why would there? It's nonsense. I stole the plot out of laziness, but then I was quite happy to have a negative example. Okay, numbers increase, seasonality, design choice to disagree with. And of course, a continuous scale like so would be much more appropriate. I also stole this one. One critique, it should start at 0, it doesn't, whatever. We'll skip this teaser here, which I'm very sad about, and we'll come to our conclusions. We saw der Mensch ist ein Augentier. Start very simple, build up gradually, increase what you're seeing. Always try to look at the raw data whenever possible. Abstractions and more complex or more involved plots do have very much their place, but always start simple and build up your understanding. Data can be continuous or categorical. Accordingly, choose your type of visualization. There's lots of research you can look up, what works best, what doesn't work. Keep in mind, some of those can be suggestive, and some of them can be like just capital B bad. Think about this kind of stuff. Please just don't do that. It's not worth it. Be, like I said, mindful of what a plot does and what it can't do, because that naturally gives rise to follow-up questions. And with that, I'm done. Thank you very much. You're always welcome to ask me questions. Feel free to hit me up in person. I will be roaming around on Telegram. On Matrix, I sometimes understand how to use it. Of course, in person, at some chaos events, I also may look like this. Not this one here, but on Congress again, if you see this guy, also hit him up. He will be delighted. Thank you so much for your attention.